Okay, this is part 2 of lesson 7.5, solving trig equations, and we're going to solve some trig equations that are a little bit more complicated. The first one is just, well, it's an actual equation where everything is kind of on the left side. So our equation here is 3 times cos theta plus 2 equals 0, and this just requires a first step, and then it's solved pretty much like examples 1 and 2. And that first step is to isolate for your trig function first. And we can do that by using reverse operations. Start by subtracting 2 from both sides. And then divide both sides by 3. And then we get something that's a little bit more familiar. Instead of 3 cos theta plus 2 equals 0, now we have an equation that says cos theta equals negative 2 over 3. That's something that's a little bit easier to solve. So our function here, cos theta, gives us a negative ratio, and cos, as we saw in a previous example, is negative in quadrants 2 and quadrant 3. So we're going to graph and have answers in quadrant 2 and 3. Quadrant 2, our solution will look like this, and our theta is rotating in the positive direction because we're looking for solutions between 0 and 2 pi, so just in the positive direction here. And let's look at our side lengths. Well, we've got opposite, which is negative 2. Sorry, adjacent, which is negative 2, over hypotenuse 3. And negative 2 and 3, those aren't special triangle side lengths. They're close, like if it was root 3 and it was on a different side, then maybe we'd have something here, but we don't have that. So what we need to do is we need to solve for our theta so we can figure out what these angles are. Well, how do we solve for theta? Well, we can just do cosine inverse to solve for theta. And if we do cos inverse, we get theta is equal approximately to 2.3. And then we have to ask ourselves, well, what did we get here with this angle 2.3? Did we in fact solve for a theta or did we solve for a beta? And you won't know until you think about what that angle represents on the Cartesian plane. Well, a half rotation would be a pi, and a quarter rotation would be pi over 2. So if 2.3 is less than pi over 2, we found a beta because we found a first quadrant angle. But if it's bigger than pi over 2 but less than pi, then what we've actually found is a theta. We've actually found our theta. So let's ask ourselves, 2.3, is that, well, pi would be 3.14, and pi over 2, well, that'd be like 1.5 something. So is it between 1.5 and 3.14? Well, yeah, it is. So we have found a theta here. Theta 1 is 2.3. So we actually found an answer just by doing cos inverse. When we go to graph an angle in quadrant 3, though, we run into a little bit of a problem. Quadrant 3, we want this angle, theta 2. We don't know what our beta is because we solved for a theta. So in order to find our beta, we have to go back to our first graph here and say, what is this beta? Well, beta would just be a whole pi rotation, a half pi rotation here, subtract this angle, right? Because if we were to have rotated to our x-axis, we would have rotated a pi, but we actually came up a little bit short. How much short? Well, that's our beta. So it would be pi minus 2.3 would give us our inside angle, our angle inside our triangle beta. Beta doesn't change no matter what quadrant you graph in. Beta will always be the same. There'll be the same beta that gives you this ratio in any quadrant. 3.14 minus 2.3 is 0.84. So our beta is 0.84. How that helps us is, well, that's what this angle here is, 0.84. Like I said, no matter what quadrant we graph in, that 0.84 will always be that inside angle. And what that does is, well, that helps us find our theta 2, because theta 2 would just be pi plus 0.84. Which is 3.14 plus 0.84 is 3.98. Our first one was 2.3. So there's our two answers. So a little bit different. We got to isolate for our trig ratio first, find out which quadrants we're going to graph them in those quadrants. If they're not Cartesian plane angles, solve for theta by doing inverse trig functions, so cosine inverse to get your angle. Find out if that angle is a beta or a theta. Since we're in quadrant 2 and our angle was bigger than 1.5 but less than 3.1, we know that we are actually finding a theta, so we found our first answer. Use your theta to find a beta. Use your beta to find your thetas in your other quadrants. That's example 3. Example 4. This is a tricky one. This says solve sine 4x equals 1/2 from 0 to 2 pi. So what this means is that we have our regular sine function, but that 4 is a k value, and what k does is it compresses the function. It takes a normal period of 2 pi to complete one full rotation and compresses it by a factor of 4. Horizontal compression of 4. So since we've compressed by a factor of 4, that means we should have 4 times as many answers in that same interval, because our function should actually do 4 full cycles within 0 to 2 pi. So instead of getting the normal 2 answers that we had been getting, we should actually end up with 8 answers. The question is, how do we get those 8 answers? Well, we can do something first. We have a relationship that says the period of a sine function is just 2 pi over k. Well, k is 4, so our period is just 2 pi over 4, which is pi over 2. And that'll come back to help us in a bit. Our period is pi over 2. Now, to simplify this equation, sine 4x equals pi over 2, we could make this a little bit more familiar by making a little bit of a substitution and say, let's let theta represent 4x. So this looks more familiar. Well, if we do that, we get sine theta equals pi over 2. And if we were asked to solve this equation, well, that's actually quite easy. We've done a question just like this. Sine theta between, this should say x, not theta, where x is between 0 and 2 pi. We've solved an equation like this before, sine theta equal to 1/2. We ask ourselves, where's sine positive? Well, sine is positive in quadrants 1 and 2. So our answers are going to be in quadrant 1 and quadrant 2. So we'd start by graphing in quadrant 1. And we'd label our triangle. Sine is opposite over hypotenuse. Opposite is 1, hypotenuse is 2. We've got 1, 2. Well, 1, 2, root 3 is a special triangle, so we have a special triangle, and that angle would be pi over 6. Right? So our theta, in this case, would be pi over 6. But we're not solving for theta, we're solving for x. We said at the beginning, let's let theta equal 4x. Well, now we have 4x equals pi over 6. And if we isolate for x, that would be divide both sides by 4. We would get x equals pi over 24. And that's actually our first x answer, pi over 24. Now, what that means is, if we rotate forward, the first time we're going to hit that value of 1/2 is pi over 24. And then we're going to hit that exact same value of 1/2 every period. So every time we go around, we're going to hit that. Pi over 6, boom, hit it. Another cycle, hit it again. Another cycle, hit it again. Another cycle, hit it again. We're always going to hit that terminal arm every period. Our period in this case is not 2 pi anymore, it's pi over 2 because we've been compressed. So to get our next 3 answers, we take our pi over 24 and we add our period, pi over 2. And that'll give us our next one, which is 13 pi over 24. To get our next answer, we do it again. Add the period again. Oops. Pi over 24, not pi over 24. 13 pi over 24 plus pi over 2. And that'll give us 25 pi over 24, which is slightly over 1 pi. And since we're going from 0 to 2 pi, we got to add it again. So that would be 25 pi over 24 plus pi over 2. And that'll give us 37 pi over 24. If we add pi over 2 again, we get an angle that's bigger than 2 pi, so it's outside the domain, so we actually stop here. And what we just generated is 4 answers. We came up with our first one. That's the first time we get to 1/2 in quadrant 1, and then we would get back to that exact same spot every period. Because remember, if we add a period to any trig function, we end up getting the same y value every cycle because it's a periodic function. The function keeps repeating. It keeps going back to 1/2 every period. Since we've compressed the function, we're going to hit that value more often. It might be easiest to describe it with a diagram, so I'm going to do that up here. On the original sine graph, for one cycle we'd have this sine function. And we would hit 0.5 right here in quadrant 1 and right here in quadrant 2. Right? And where we would hit it would be pi over 6 and 5 pi over 6, just before pi. And we'll get that value when we do the other quadrant. But what we've done here is we've compressed the graph. So instead of just having one rotation, we have, that's 1, 2, 3, 4. We have 4 times as many cycles in one period. So that same 2 pi, we actually have 4 times as many cycles. So instead of just having 1, 2 times that we hit 0.5, we actually hit 1, 2, 3, 4, 5, 6, 7, 8 times. And we hit it in quadrant 1, and then in quadrant 1, and then in quadrant 1, and then in quadrant 1, just compressed to a scale of 4. So how we come up with those answers is, well, how we come up with the answers if we hadn't compressed is, well, we draw another cycle, and that would take us to 4 pi. And the next time we get 0.5 from here would be right here, which is just, well, pi over 6 plus 2 pi. We'd add the period to get to this next point. So we do the same thing with the compression. To get to it the first time, well, we solved for it, that was pi over 24. To get to the same spot on the curve the next time, we add the period. Well, the period is this time, since we're compressed, is pi over 2. So the next time we get there is pi over 2. Plus where we got there the first time, which was pi over 24. That's how we get our 13 pi over 24. And we keep getting answers every pi over 2, so we just keep adding the period until we get an angle that's outside the domain. We don't count that angle, and we finish with all the angles that fit in that domain. Those are all the quadrant 1 angles that fit the domain. Let's look at the quadrant 2 angles. Quadrant 2, we have our Cartesian plane. We have our theta. We know that sine opposite 1 over hypotenuse 2. Same beta, pi over 6. In this case, our angle theta would be 5 pi over 6. Because it'd be pi over 6 short of a pi rotation. So our theta would be 5 pi over 6. But theta, we said, was 4x. So we replace theta with 4x. And now we divide both sides by 4, and we get 5 pi over 24 as our first x value in quadrant 2, or our fifth x value. And then that would be this spot on the curve. The first time we hit it on the downward spot on our curve. To get this answer, and this answer, we just add pi over 2 to the first answer to get that answer, add pi over 2 again to get that answer, and add pi over 2 again to get that answer. We just keep adding the period. So to get x6, we would take 5 pi over 24 and add pi over 2. And we would get, well, over 24, that'd be 12 over 24. 12 plus 5 is 17 pi over 24. And that would be our 6x. And to get 7, we would add pi over 2 again, and that would be 29 pi over 24. And to get it again, we would add pi over 2, and that would give us 41 pi over 24. If we add it again, we get an angle that's much too big, so it doesn't fit in the domain. Much too big is bigger than 2 pi, or bigger than 48 pi over 24, so it's outside the domain. So we stop here at our 8th answer. I guess x8, not x4. So we have 8 answers. We have our first 2, and then we've just added pi over 2 3 times to our first one to end up with our next 6 answers. So this is when we have a compression. If we have a stretch, well, then the opposite would be true. Our answers would occur, if it was a stretch by a factor of 2, they would occur half as frequent. So that would mean you'd only get one answer. If there's a stretch by a factor of 4, you might not get any answers unless it's in the first quadrant, in which case you'd get one answer. So stretching and compression can affect how many answers you come up with. General strategy, though, find out what the period is first. Let theta equal whatever's inside the function. Figure out what quadrants your function's positive or negative in, depends on what the equation is. If it's equal to a positive ratio, you're looking for where it's positive. Equal to a negative ratio, looking for where it's negative. Graph them in those quadrants. Solve for thetas just like you did in the first examples. Replace theta back with what you replaced it with in the beginning. In this case, it was 4x. Solve for your first answer, and then add the period as many times as you can to still fit the domain. If it was going backwards to negative 2 pi, then you'd be subtracting the period as well and coming up with our answers rotating backwards. Do it until you find an angle that's outside the domain, scratch that one because it's not inside the domain, and then go to your other quadrant, find your first angle, and then add the period until you get angles that are outside the domain, scratch that one, and you're done. In this case, 8 answers. Okay. There's a practice example, sine of 2x equals 1 over root 2. Since it's 2x, that's just a compression by a factor of 2, so you should expect 4 answers when you try this question. Try it using the strategy that we just discussed for example 4, and hopefully you're successful. If you're not, we'll tend to it in class. But again, thanks for watching, and I'll see you next time.